Good morning. Today's topic is relationship between Fourier and Walsh series. In the last lecture, we have discussed about what Walsh series is all about, and we have also seen what is significance of Walsh function and what are the properties of Walsh functions, and we have also seen the representation of Walsh functions. And once we have determined the Walsh functions, we have seen how to represent any signal in Walsh series. In today's class, we will discuss the relation between Fourier and Walsh series, and we will determine the relation between the Fourier coefficients and the Walsh coefficients. I'll start with the Walsh series, which we have started in the last lecture, and then I will move on to Walsh coefficients, and then we will move on to determining the relation between Fourier and Walsh coefficients. Now, coming to the introduction, as we have seen that any signal f of t, any signal which can't be having, which may not be having any particular described or specified expression, mathematical expression, it can be represented in terms of either Fourier series or Walsh series. Two important series which are generally used to represent an undefined signal. Now, in Fourier series, we do employ trigonometric functions, whereas in case of Walsh series, we do employ square functions for representation of any signal, periodic signal. Now, this is what I have mentioned here. Fourier series expresses a periodic function as a sum of sine and cosine functions with various frequencies, and it is often used in signal processing and other engineering applications. Whereas Walsh series, it is also a representation of a periodic function, and it is a sum of Walsh functions, which are basically piecewise constant and orthogonal functions, and this is exclusively used in digital signal processing. Normally, when the signals being processed are either 1 or 0, or if they are piecewise constant, then Walsh series will be helpful for representation of that signal. Even though both are of different formats, they provide a way to decompose any periodic function into simpler components so that we can analyze the harmonics which are present in that particular signal. This helps us easier in particularly communication sector and also signal processing sector and also in control systems where we do need to design proper controllers. So this is the Fourier representation of any periodic signal. These are the F1, F3 and F5 on. These are the sinusoidal components, whereas these indicate the cosine components, whereas this is a DC component, what we call it as. Now these two particular, they are called as fundamental components, coefficients of or terms representing fundamental components. Whereas this is DC component. These two represent the second harmonic components. Likewise, any signal, it is represented in terms of trigonometric function sine and cosine, and it will be leading up to infinity. Similarly, see the values of coefficients which we have mentioned earlier. The DC component coefficient, this is F0, this is determined using this particular equation, whereas the sine components, which are basically for n is equal to 1 to 3, for n is equal to 1, its value is 1, for n is equal to 2, its value is 3, 5, 7, like that. Whereas here it will be 2, 4, 6, 8, like that. This is what I have shown you in the last slide. So these are sinusoidal components, these are cosinusoidal components, and this is the way how you will be determining the Fourier coefficients. Whereas on the other hand, Walsh representation of a signal, see, If the same signal, it can be represented using Walsh series, and this is the representation of Walsh series. This is the Walsh function, and this is called as the Walsh coefficients. Now, if you compare these two equations, both the equations, the Walsh coefficient representation and the Fourier coefficient representation. Now, W naughts, see, the previous one, this W naughts, see, this is the Walsh coefficient, right? This is the Walsh function. So, how you determine the Walsh coefficient? This is given by this particular formula. This is the representation of Walsh coefficient, where f of t, it is your term. Now, if you represent f of t in terms of Fourier series, then you can determine the relation between the Walsh coefficients and also the Fourier coefficients. This is what I have done here. See, the same expression of wk is equal to 1 by t integral t1 to t1 plus capital T, f of t, this is Walsh k of t by t dt, right? So this is the Walsh coefficient for the kth coefficient, right? Now what I am doing is I am replacing this f of t in terms of Fourier coefficients. Now you know f of t in terms of Fourier coefficients, you know that it is f naught plus root 2 f1 sine omega naught t plus root 2 f2 cos omega naught t. Similarly, plus root 2 f3 sine 2 omega naught t, like that, f4. So these do represent the fundamental component, these two represent the second harmonic. Now I am just replacing f of t here. So this is the expression. Now here I am replacing k is equal to 0, and here I am replacing k is equal to 1. So if I generalize the expression, this is the term for wk. Right. So now if I do represent these things in a matrix format, now w naught to wk, and if you want to go up to n minus 1, this is the order. Right. Then what is a naught order? This is the A matrix. Now as I have shown you, see, W naught depends upon this F naught, F1, F2, F3, right? And W1 is also depending upon F naught, F1, F2. See, which means that every term depends upon F naught, F1, F2, F3. See, what is then different? See, these are different. So this is what I am trying to represent in terms of A now. So if I represent the other terms in terms of A, then this is your Walsh coefficient matrix. And this is your Fourier coefficient matrix. Now both are linked using this particular matrix, and the linkage is represented by A matrix. Right. So now what is A now? As we have seen, if I compare both the terms, this is A matrix. So if you want here 0, then this is the term. If you want it here 2 minus 1, then it can be, it is an odd number, so you will be getting a sine term, sine and if it is even number, then it is cos term. You can just simply compare the above expressions and you can write them. So in this way, you are supposed to determine the A coefficients. Once you determine the A coefficients, and if you do have the Fourier coefficients, then you can determine the Walsh coefficients. Otherwise, it is vice versa. So since the equations are very large, we will try to simplify them. So for making this problem simple, what I will be doing is, I'll be this t by t, whatever term it is, I'll be taking it as t dash, and see here. And this t1, I'll make it as 0. So this will become 0 plus t. So I'm just trying to simplify this term. So t by t is equal to t dash, right? So what is this? dt by t is equal to dt dash. So I can just represent these things. So now this particular expression, now what does it become? It will become, this is 1 by t integral 0 to capital T. This is Walsh 0 comma t dash. This is dt, right? So from here dt I can write it as t into dt dash. So I can remove this term. So I can just write it as 0 to capital T Walsh 0 dt dash. Similarly, I can replace the other terms also. Yeah. Right. So here there was a 2m term. So that for that one also I am taking a replacement. See, I am taking a replacement. M is equal to k by 2. So this will help me out to simplify my expressions. Right. So when you are able to calculate the A coefficients, as already been said, W is equal to A into F. This is the simplified expressions for A. Once you are able to calculate A, if you do have the Fourier coefficients, then you can easily calculate the Walsh coefficients. On the other hand, F is equal to A inverse into W. You can use this term also. See, it is easier to calculate Walsh coefficients, right? So once you do have the Walsh coefficients, you can employ this particular matrix and then you can calculate the Fourier coefficients, right? So Walsh functions are basically used to represent periodic functions with the help of orthogonal square waves. And Walsh function is consequently useful when particularly the signals take the form of logical pulses. And it is easier to calculate Walsh coefficients. So once you do have Walsh coefficients, calculate A matrix and Fourier coefficients are obtained in this fashion. Right. So once you do have the Fourier coefficients, then you can estimate the fundamental component, phasor of the fundamental component, and also phasor of the other harmonics. So that's it. So I hope that now you are able to describe the relation between Fourier and Walsh coefficients. We'll solve the problems in the class on Fourier and Walsh coefficients. Thank you.